So, good morning students. So, in this lecture, we will discuss about the class B amplifier. So, we know that in the class A amplifier, the conduction is in between what? It is 360 degree. So, in the class B amplifier, the conduction is 180 degrees because of the Q point. As we are maintaining the Q point in the cutoff. Here, with the follow from where it cut off. So cutoff region is this one. So Q point, if I maintain Q point at this place, so only 180 degree waveform will be conducted at one transistor. So to conduct the 360 conduction, we are using the two transistors. So class A amplifier. So in the class A amplifier, what if if we require a full conduction, that is nothing but half cycle. If one transistor will conduct half cycle and second transistor will conduct half cycle. So we require a half cycle for this one and half cycle for this one. So as far as NPN transistor is concerned, it will conduct a negative half cycle, and the EMP transistor inverter will conduct a positive half cycle. So from the NPN and PNP, how to remember? NPN negative start negative conduction, PNP positive half cycle will conduct. Okay, so you can remember like this one. So the efficiency maximum is 78.5%. Keep in mind, the class B amplifier efficiency is 78.5%. So efficiency is given by power output AC divided by power output DC into 100%. So maximum power output is given by VCC square divided by twice of RL over there, and maximum power VL is equal to VCC. That is nothing but the voltage of load is nothing but the VCC. If you are giving this one, we are getting the maximum power. So maximum DC power is nothing but the VCC maximum into maximum IDC is given by VCC into twice of VCC divided by pi. Pi we are getting for 180 degree conduction into RL. So if you are multiplying, so it will give you twice of VCC square divided by pi of RL. So maximum efficiency is given by twice VCC square divided by pi RL. So transformer coupled push-pull amplifier. What is exactly meant by push-pull amplifier? That we'll see. So here we are using the NPN transistor Q1, and here you are using the PNP transistors. Okay, and so this is nothing but an input. So that is divided by like this one. And the R1 and R2 are forming the biasing network for that. So biasing network will give you the Q point voltage. Q point voltage. We know that this this transistor, both transistors are nothing but what arrow is outside, so indicating nothing but PNP transistor, CNP transistor over there. Okay. So this circuit is nothing but a push and pull over there. What is the push and pull that we'll see over there? Okay. And at the output again we are using the one transformer and the secondary winding connected to my load over there. So here this is N1 and here is nothing but N1. That is nothing but turns ratio at this point is equal to turns ratio at this point over there. Second point to this one. And the current is I1 and the current is I2. So during the positive half cycle, what will happen? Positive half cycle of input AC cycle. The transistor QN, the transistor is nothing but this transistor here. You will find a Q1 is nothing but my conduction and Q2 is off. This transistor will conduct and this transistor will off. And then during the negative half cycle of AC input, the transistor QT will conduct. So this will conduct and this will off over there. So this is nothing but work. Again, one is pulling and one is pushing. And pulling, one is pushing. So this will happen due to this. We know that this circuit configuration is called as class B push pull amplifier. Class B push pull amplifier. So due to which we are getting the full 360 degree conduction. But one phenomena occurs over there, that is nothing but the crossword distortion. Crossword distortion. So if one transistor is turned on, one transistor is turned on, and that time second transistor is turned on, due second transistor due, and after that it will switches. That is nothing but first of all Q1 is on, second is off. Second case Q2 is on and Q1 is off. In the transit time, you will find the gap over there. Here you will find a gap that is shown by the circle. So this is nothing but a crossover distortion. This is nothing but my crossover distortion. Due to that, we are using the Darlington pair, and that is nothing but the quasi-complementary push-pull amplifier. So here the Darlington pair is used. Here is the dialectal pair. This is nothing but NP transistor and this is nothing but PNP transistor. So if we are using such kind of configuration, so this increases the output power capabilities. Output power capability it will use. So it's okay. So what are the harmonics? So harmonics is the integer multiplication of fundamental frequency. If the fundamental frequency is 5 kilohertz, that is nothing 5 kilohertz, 5 kilohertz, 5 kilohertz, and the first harmonic is nothing but the 1 into 5 kilohertz, second is nothing but 2 into 5 kilohertz, third harmonic is 3 into 5 kilohertz, fourth harmonic is 4 into 5 kilohertz. Okay. So note that first and third harmonics are called odd harmonics, and second and fourth are called as even harmonics. Second and fourth are called as even harmonics. Okay. So harmonics is nothing but what? One frequency continuously occurs. One frequency continuously occurs. That is nothing but the 5 kilohertz suppose. And if you are multiplying with 5, 2, like this one, multiplication of that one, 10, 20, 30, 50, multiply with 5. So that is nothing but one. What is the harmonics? So first harmonic, second harmonic, this will occur in the amplification. So harmonic distortion will happen in this case. So how harmonic distortion? Suppose this is not a distortion input signal. This is the distorted input signal. So this is nothing but my VI sin omega t. This is nothing but my input cycle over there. So second harmonics is occurred like this one, and third harmonics like this one. Like this one will happen. If you are taking the overall effect, then we are getting the harmonics over there. So our signal is like this one. Yes, the signal is like this one we are getting. So how to calculate the harmonic distortion? So harmonic distortion calculated by that is nothing but the A of n divided by first harmonic over there into 100%. If you are calculating, if you want to calculate the nth harmonic distortion over there, where An is the amplitude of fundamental frequency and An is the amplitude of highest harmonic. Here it should be 1 over there, and the total harmonic distortion is calculated by under root of d2 plus dt square plus dt square plus up to 100 over there into 100 over there. You have to calculate like this. The power transistor degradation curve, derating curve. So how it is? If the temperature is increasing one, if the temperature is increasing one, and here under this graph you will find it is equal to maximum total device dissipation. So maximum power dissipation over there. So this curve is like this. If the temperature is increasing, it will you will find a maximum efficiency over there. So it is constant over there. And if the temperature is above near about 75, so it is possibly decreasing. The dissipation of power is possibly decreasing, and 200 it will become 0 over there. So temperature is very very essentially what you can say essential term. If temperature is increasing, your efficiency will be decreasing over there. In the see the class C amplifier. In the class C amplifier, it conducts less than 180 degree. In order to produce the full wave of class C using LC tank to provide the full ACC. So less than 180 degree conduction is there. So in this case, we have to use the LC circuit. So full 360 degree conduction will occur over there. So class C amplifier uses extensively in the radio communication circuit. The class D amplifier. So is in the class D amplifier normally it is used a pulse waveform. So it is used in the DC circuits where we are using the pulses over there. So its efficiency is more than 90%. This is all about the power amplifiers we have discussed from class A, class B, class AB, class C, and class D over there. So if you have not watched my previous lecture, so please go to the playlist and you can watch the entire video series. So thank you very much for attending this lecture. Thank you.